we would like to extend our knowledge of finding and identifying critical points to functions of several variables. In previous videos, we have considered the notation of partial derivative of a function and how to evaluate it. The situation is also the same for functions with n input variables. In general, when we evaluate the partial derivative of a function with respect to an input variable, we treat all other input variables as constants. For a function with n input variables x1, x2, up to xn, you will expect that there are a total of n first-order partial derivatives of f with respect to each variable. If we construct a vector in Rn using these partial derivatives as the entry, we get a vector in Rn which is called gradient of f. This vector, the gradient of f, can be regarded as a vector collecting the first derivatives of the function f and give us important information on the function. For example, if the function contains three input variables x, y, and z, we have a total of three first-order partial derivatives, namely f sub x, f sub y, and f sub z. The gradient of f in this case will be a vector in R3, namely f sub x I plus f sub y j plus f sub z k. In previous video, we noticed that a critical point is a point where all the first partial derivatives of f are zero. Geometrically, this means that when we consider the cross-section along the axis of each input variable, the function has a slope of 0 at that critical point. If we use gradient of f to represent this, it means that the gradient of f is a zero vector at the critical point. Whenever we want to find the critical points of a function, we first compute the first derivative of the function with respect to all input variables one by one and form the gradient of f. Then we solve for points that are zero for the gradient of f. Please make a pause and attempt the following example by yourself. The solutions will be given afterwards. Please refer to the solutions by yourself. After we obtain the critical point, we wish to identify its nature. It can be a local maximum, local minimum, or a saddle point. We mentioned in previous video that a saddle point is a critical point which is neither a local maximum nor a local minimum. For example, it may be a point which has a local maximum when we consider the cross-section parallel to the x-axis, but a local minimum when we consider the cross-section parallel to the y-axis. The word saddle is the name of the seat which you place on the back of the horse so that you can ride the horse comfortably. The items introduced in the following few pages are to prepare us to the theorem for finding local extremum and saddle points of functions with several variables. First, we consider the Hessian matrix. It is a square matrix which contains all the second partial derivative of a function. If the function has n input variables, we shall have n first-order partial derivatives. For each first-order partial derivatives, we have n different ways of further differentiating it. Therefore, we have a total of n square second-order partial derivatives, and the Hessian matrix will be an n by n square matrix. Please refer to the correct order of placing the derivative in the Hessian matrix as shown in the notes. For most functions in practical application, the expressions are the same if you interchange the order of the second derivative with respect to the two different input variables. Therefore, the Hessian matrix in this case is a symmetric matrix.
Please make a pause here and attempt the example here by yourself. The solutions will be given afterwards. Please refer to the solutions of the previous example by yourself.
Next, we consider submatrices of the Hessian matrix and find their determinants. A submatrix is a matrix which is formed by extracting certain rows or columns from a matrix. A submatrix is not necessarily a square matrix, and it is not necessary to extract columns or rows from the top left-hand corner. However, in our context, we only need to consider submatrix of the Hessian matrix, which are square matrices, and formed from selecting the top left-hand corner from the Hessian matrix. We denote by H1 of vector X to be the smallest 1 by 1 square submatrix, extracting only the elements from row 1, column 1 from H of X. We denote by H2 of X to be the 2 by 2 submatrix, extracting the elements which locates in the first two rows and first two columns from the Hessian matrix H of X. In this way, we can form H3 of X and so on until Hn of X, which is a submatrix of Hx and which is also Hx itself.
For each of these submatrices, we compute its corresponding determinants, and the results are called leading principal minors, which are denoted by delta K at point X. Please make a pause here and attempt the following example. The solutions will be given afterwards. In earlier page, we have already obtained the Hessian matrix of this function. Now we continue to obtain the submatrices of this matrix and the corresponding leading principal minors. We are only interested to find submatrices which are also square matrices and taken from the top left-hand corner from the original Hessian matrix. The first submatrix is a 1 by 1 matrix H1 taken from the top left-hand corner of H. So this gives a matrix with the entry 10. The second submatrix H2 is a 2 by 2 matrix taken from the top left-hand corner of H. We get this 2 by 2 submatrix. And the last submatrix we are interested is a 3 by 3 submatrix taken from the Hessian matrix. But since the Hessian matrix itself is a 3 by 3 square matrix, therefore the submatrix H3 is also the Hessian matrix itself, which is this one. Now we would like to compute the corresponding determinants of each of these submatrices. The leading principal minors are the values of all these corresponding determinants, and we have the following results.
We are now ready to refer to the theorem for identifying critical points of a function with several variables. This theorem is called the second partial derivative test for function with several variables. It applies to a choice differentiable function with the critical point at P. First, for each of the delta K computed at the critical point P, if the product of its value times -1 to the power K is positive for all k equals to 1 up to n, then f has a local maximum at the point P. Next, if each of the delta k computed at the critical point P is positive at P, then f is a local minimum at P. Thirdly, if the determinant of the Hessian matrix computed at the critical point P is non-zero, but none of the previous condition holds, then f is a saddle point at P. Finally, if the determinant of the Hessian matrix computed at the critical point P is zero, it is inconclusive. Please notice that if we apply this theorem to functions with two variables, the statements here are exactly the same as the theorem we mentioned in the last video.
Please make a pause here again and try the exercise here by yourself. The solutions will be given afterwards. Please refer to the solutions of exercise 1 by yourself. The graph of the function g, which is x squared minus y squared, is shown here for your reference. Finally, please refer to the solutions to exercise 2 by yourself. The graph of the function f is shown here for your reference.